So what we're doing is we're building a distributed hypervisor on FreeBSD. And this is something we internally call a hyperkernel. Obviously, at this point, there's no marketing behind it. But we want to sort of differentiate what we're doing from a traditional hypervisor. If you want to know what a hyperkernel is, I'll be explaining that in a minute. But distributed hypervisor, and we put that across as a thin layer on a bunch of FreeBSD nodes. And I'll be saying more about that. So all of us, including Peter, actually run FreeBSD and VMs on our laptops. Although I run, obviously, I run OS X at home, which is pretty close. All right, so we're a post-Series A startup. We raised over 8 million in our A round. And what we do is we eliminate the need to re-engineer applications to run them at scale. So now traditionally, if you have an application where you need data in memory and that doesn't fit on a traditional server, what you do is you scale that out across a cluster. You shard the data, you split up the queries, you do something like MapReduce or some other technology. And that stuff works. Sometimes it works really, really well. But you have to rework your application. You almost always need a data scientist, at least at the start. And if the thing is rapidly evolving, that's a lot of work. And we know from the industry that people in all sorts of situations run into trouble doing that, right? Either they have to keep re-architecting, or they run into hot node problems. Say at Facebook, they published a paper on this where they're doing their analysis, but their analysis doesn't fit into a 256 gig node. Their performance falls apart. And so what TitleScale does is we take a different look at that, is we take that same scale out, but through the distributed hypervisor, we turn it into a single system image. So I'll talk more about that. But basically, we boot a single virtual machine across the cluster. And then we run a single guest in that VM. But the guest has the resources of the entire cluster at its disposal. Okay? And I'm going to run this video. And hopefully that'll make some sense. No, it's not going to do. I don't know if this is going to play the sound, but we'll see.
What's the audio in?
Yeah, how do you do the audio in?
I will go.
Ah. So I have that on my laptop, so if I just hit play.
No, I think you need to. No, you're on one. Can you talk to it?
Maybe I'll do this. Hang on.
HDMI is not going to play.
Okay.
You go on the VGA.
When it comes to the potential of what can be accomplished with big data, the sky is the limit. From business to medical research, data can help us learn, grow, and solve big problems. But when it comes to analyzing your data quickly and completely, there are huge limitations. In order to process data in real time, you need to be able to scale your computer to the size of your problem. Small problem, small computer. But the bigger the problem, the more data you have, which means the more RAM, processors, and storage you'll need. But a single node can only hold so much. If you could just build your own computer to scale to your problem, you'd be good to go. But that's incredibly expensive. The other option is to get lots of nodes to chop the problem up, which means rewriting your application to distribute the data and the queries to each node. But that's incredibly complicated, and it's still super expensive. With all these limitations, you can't even see the clouds, let alone reach for the sky. Until now, thanks to TidalScale. TidalScale is a revolutionary new software layer that gives you supercomputing power to solve giant data problems at a fraction of the cost. TidalScale runs between your hardware and your OS, allowing you to string together as much commodity hardware as your problem demands. Then instead of the divide and conquer method, it operates as a single machine with a single OS. If you need more RAM, CPU, or storage, you just add it. No application or OS change is necessary. Just a bigger computer for a bigger problem. And ultimately, when you can scale your computing power this easily and this affordably, there's no problem too big for you to tackle, which means the sky really is the only limit. So go to TidalScale.com to learn more. TidalScale. Scale your computer to your problem.
All right. Yay, okay. All right, so a little bit more about us. We've raised money from Hummer Windbud, Bain, Samsung, Citrix is an investor, thank you, Sapphire Ventures. We've got a great board of advisors, Fred Weber, former CTO at AMD, also on the board for MIPS. He was involved in 3Leaf, which was a similar idea to what we're doing, but it was done in hardware several years ago. Gordon Bell led the development of the VAX at DEC. And Carl Waltzberger, who was an early on the team at VMware. And Mark and Jeff didn't mention this, but they're also VMware alumni. Now about the team, this is something, I actually struggled with this slide the most, so it's hard to talk about our team. You know, we've got this very diverse background in systems infrastructure, you know, kernel, networking, storage, hypervisor, security, and UI. There's about 10 of us, and we have 300 plus years of engineering experience. That tells you something about the team. Also, from a business development angle, we are, for the most part, serial startup alumni, right? And Tom and I started making the list of how many IPO or M&As we were in, and we said, that's enough, 10 plus, we'll stop there. Right? So we've done this before, but I have to say personally, this is one of the most exciting infrastructure projects I've been involved in, and I've been involved in a lot of them. And this is by far the best engineering team I've ever been on. Right? It's really been a superior team. And so to give you an example of how I think about it, these were the pictures that came to mind. Right? So, you know, we're part Avengers, we're part Mission Impossible. But this is actually out of date. We've got more members, but this is who we are, right? And we're doing something really hard and really cool, and we're very excited about doing it. All right? So, obviously our starting point, we're here talking to you, FreeBSD and Beehive. All right? Now, to do what we're doing, we aggregate the resources of the cluster. And one piece of technology we had to change or modify to do that is we had to create our own resource bus for all the resources of the cluster, because we don't have a physical hardware bus, obviously connecting all those machines. What do we really have? 10 gigabit Ethernet. So we use that 10 gigabit Ethernet to connect the machines and to mobilize all those resources. And I mean that, you know, all those resources, CPU, I/O, memory, all right? So that's where we had to modify that Ethernet driver. In addition, we've made changes to how, you know, we, the host, namely FreeBSD in this case, schedules the virtual CPUs of the guest, right? For those of you who follow the list, we see there's actually people working on gang scheduling as it relates to Beehive. It's a similar issue. When you're running the guest, you need to run the vCPUs at the guest in such a fashion that they're all getting access to the resources, right? And ideally, at the same time and in a fair way, right? But in our case, spread across the clusters. That's a different problem. The idea being, though, that we deliver a software-scaled computer. So another way to think about what we're doing is we're just delivering a piece of software that turns a cluster into a computer, you know, a bigger computer, right? And this is what we call the hyperkernel, right? It's that thin layer that runs above the hardware.
You
Right.
call it BFC.
Yeah, we also call it a BFC. The big fucking computer, right? So if you think about this, we typically run in our internal development 3 to 5 nodes. We've booted 10 nodes. The goal is much bigger than that. So, you know, we're aiming at, you know, 10 terabyte systems right now, but down the road we imagine getting to 64 terabytes and beyond. And not hundreds of processors, but 1,000 processors or more.
And this is a single system image?
It's a single system image. Exactly. So these are the pieces that you have to deliver in order to make this real, right? You have to have distributed coherent shared memory. We boot an unmodified guest. So we take CentOS or Red Hat today or FreeBSD, take the ISO, boot. Okay? It comes up and sees what we want it to see, right? And so this enables the customer to size the computer to the problem. So they don't have to chop up the problem or re-architect their software, right? They just run it. And we've done this with SQL, we're doing this with R. You know, you just run your application. You don't have to change it. As I was saying, we currently support CentOS and Red Hat version 6. And you know, Jason runs the support group. He's also the support group. So we're not supporting a lot of guests out the door. So you know, we have a so-called community. We make sure other things are working, but we're not planning to support them day one, you know, with 1.0. But we make sure they work. FreeBSD, we make sure it works. Oracle Linux, we're making sure it works. Things like that. So this gives you a little bit. Is it okay with the light on? So this is more or less the picture of a TidalScale computer, right? You've got your typical server blades in a rack. I'll stand over here. Management networks. So in a typical data center, I'm sure all of you know this better than me. I'm sure the Netflix guy knows it 10 times better than me. But you have your servers, you have a management network, and in our case, we have this backplane, right, of a 10 gig E network that we actually use to stitch together all the nodes. That becomes our resource bus. And then we provide the guest an external network as well. So once you boot the guest, you know, you're just on Linux or FreeBSD. You have networking, you have all the things you're used to having. It's configured. We have this management console application we call TSAdmin. TSAdmin is what allows you to configure the pod. We call the cluster a title pod, and set up its size, set up how many CPUs, how much memory, all those different things. And right now it's a command line interface tool. It's scriptable. In process, we've got a REST API and a GUI that'll be running on top of it. But we're really looking at it from the data center point of view, and we expect people to integrate it with their data center operations. All right. So, you know, it just makes that computer big, right? You get all the resources. So internally, let me just talk about this a little bit. So when we started this project, you know, the first thing we did was, in our case, we're a Mac shop, so we run Fusion, and we ran Beehive in Fusion, and we just said, okay, we can run Beehive. And then the first task was to modify Beehive enough to stitch together multiple virtual machines. So I won't show you it right now, but I can show you later a VirtPod, which is basically you know, a handful of virtual machines running on Fusion that we then stitched back together into a single machine.
Cool.
Okay.
Very cool.
And what's nice about this is it gives you a rapid development environment where you can try things out right on your laptop, right, and just see what goes on. Obviously, for performance testing and performance tuning, that isn't sufficient. And so we actually have a bunch of hardware now where we boot and run our software and run guests on that software. And that's where we're running our big scale test today. All right, so I'm going to show you a quick demo. And let me do that. Somewhere. You know, believe it or not, I had prepared ahead of time so I wouldn't have to do this. But I'm not seeing it now. There it is. Okay. So what I did over here, so I'm running the guest. And to save a little time, I went ahead and booted it. So what you're seeing here is this is a CentOS boot. Okay. So in the blue window, I started up a title pod across 3. I tried to fix that. It doesn't seem to help. So up here on the left in blue is a CentOS guest. And really this is the same thing you would see, or very similar to what you would see if you booted CentOS on Beehive, right? It just boots, right? It sees the hardware that we emulate, lie about as a hypervisor does. But in our case, the hardware is 3 different computers sitting in our colo right now, right? So this is top, right, showing that system. And over here, I've logged into that system. And if you're a Linux guy, that's what you've got. You've got Linux. It's just Linux with half a terabyte or a terabyte or 1.5 terabyte memory or more. Okay? Whatever size you need. It just looks like Linux to you once you're up and running. Right? And I'm happy to show more about that. I just don't want to. Okay. So initial market for us, for those of you who are interested, I know this is mostly a technical group, but we all care about this anyway. Data analytics looks really big for us for obvious reasons. But we're also finding a lot of interest from the SQL community, right? Because you can just basically take SQL, memcache it, or, well, not memcache is the wrong term, but put it into memory, right? And now you have all your database in memory, right? And we've seen enormous speed ups by doing this, as you'd imagine, okay? And then further down, this is where we're gonna come out in 1.0 supporting these types of technologies. But then we see EDA, for instance. There's a big, not a huge opportunity in terms of the number of customers, but they need it. They're desperate to have something like this in EDA. Genomics is another area. So the sort of problems that are hard to shard, is how I put it, are great for us. Okay? And there's a lot of problems that are hard to split up and do divide and conquer with. For those of you who haven't gotten a tour, this is what our development looks like. We're back in the back part of the office. I didn't know if people were interested in how we're doing this, but I can talk about GitHub and Jenkins and target process and Slack. We have people here who are local and remote. We basically live in Slack all day long. Harry can talk about Jenkins. We all can talk about Jenkins. So Jenkins is our overlord. Everybody engineering at this point pretty much works for Jenkins, right? So Jenkins tells us if our builds are good. Jenkins runs our initial performance and smoke tests. And this way on a commit by commit basis. Well, it's every 15 minutes, right? So it may aggregate a few commits. But similar to what BSD does with Tinderbox, right? We're doing the same thing. Jenkins picks up our commits, builds the system, runs through a test matrix, and we get to see what's going on. Right? And it's nice to have a robot doing that, because we all know how painful it is to do that by hand, right? Anybody want an Agile talk on top of this? I can talk about Agile. But what I will say, and no, we don't have money from Andreessen Horowitz. So I'm not plugging Slack because of that. We really find Slack very useful. So I'm sure everybody has some kind of team chat, but Jason's done a lot of the Slack integration, so has Harry. So there's a channel that Jenkins is feeding into. Our Agile tool is target process, so target process is dumping into a channel. And it's just nice to have one place where we see card status changing, where we see build statuses and things like that all in one place. I find it tremendously useful. I think everybody does at this point.
Oh, Salesforce integration as well.
And Salesforce integration, but we don't see that yet because we're keeping Tom from, we haven't released yet. We're holding him back. He's chained.
Do you use GitHub for issue tracking?
No, we're doing issue tracking and target process. And then we have, for tech support, Zendesk. But we're not using it yet because we haven't deployed to a customer. So the customer interface will be through Zendesk, and that also has an integration back to Slack, and I think target process as well, correct? Or we haven't done it yet?
No, not planning on doing that. You really want to do that by hand to understand things.
Right, that's right. All right, and that's it. Thank you.
Can we ask questions?
Yes, please,
All
ask
right.
questions.
Go first. All right, so you had a cool window there of a Linux VM with
Yeah.
half a terabyte of RAM. That's
Or
great.
could have been, yes, yeah.
Okay, that's great. So we got a lot of storage in there.
Yeah,
What about storage?
all right.
How's storage work?
Well, right now, well, the safe answer is we provide the VirtIO interfaces to the guest. All right. So one thing a customer can do is they can hook up a lot of storage,
Okay.
right? Or they can hook up a single array. Now we do IX systems, thank you. We internally are using your NAS, and then we have iSCSI targets that we advertise to the guest.
Okay.
And that's what we're doing.
Okay.
Anybody could do the same thing. There's also interesting ideas where we could integrate in the hypervisor layer, thank you, with people who provide high-end storage. And so that way, as a hypervisor service, you know, faster emulation path, faster block storage, faster whatever, than what VirtIO does.
Okay.
Yeah.
Probably worth making one sort of philosophical comment, which is basically we provide a machine. The guest operating system can do anything a guest operating system can do with things like storage and networking and so forth. So except for the hardware acceleration point of view, you've got a really big machine with a lot of channels, essentially.
Right.
Yeah, but if the guest wants more storage, I mean, it has to get the storage from, you know, the host, right?
Well, it gets them from the hardware. The host, FreeBSD doesn't necessarily get in the way in a
Okay.
serious way.
If we,
We expose we could expose physical disks. To
Right.
Yes.
Or we could expose 10 gig Ethernets to the guest and let the guest do iSCSI on top of that through us, and we don't even know it's storage. You know? And there's lots of ways, lots of options, because it's just a machine.
Yeah.
So is a customer going to get a title pod and then start attaching their storage to it?
We expect to go into a data center.
Right,
So the customers we're talking to have lots of computers
right,
and lots of storage.
all right,
And they're going to install our software and stitch the servers into one big computer. All of the storage that those individual servers are attached to are then available to the guest, right? In our case, through the VirtIO interface, but also could be directly via iSCSI, for instance. Right? Yeah.
So you have a bunch of servers. Those servers may have storage on them, okay? That storage, we then boot this guest OS, we lie, and, you know, we look like hardware to the guest. So anything you can do from the guest, which is what David was saying, you can still do, okay? But you can also do it remotely using, you know, file servers. So you have complete freedom to configure your storage any way you want.
So basically, the host storage is available to as VirtIO devices, and then the guest can use those through VirtIO, or the guest can go off and do iSCSI or whatever other is out there.
Yeah, we don't require, and in fact the machine is running on
Right.
doesn't need to have any storage for running the hyperkernel.
Right.
So we actually Pixie boot the hyperkernel
Gotcha.
and give it its initial program load over
NFS.
NFS right now, I think, or it could be iSCSI.
Right.
But, so essentially, all the real hardware on the machine and all those external network connections
Gotcha.
are just handed through to the guest operating system, which can use any software it likes.
Gotcha.
Yeah.
Okay.
Yeah.
The only thing we hide is what he called the bus.
We hide the resource bus, but we also hide our metadata structures and our text, our hypervisor code itself.
Yeah.
So we wall that off like any hypervisor would,
Sure.
and then the rest of the machine is the guest's.
So,
The rest of all the machines is the guest, potentially, yeah.
right, okay. So speaking of the resource bus, so you've got your host title pods. And so they've got a network connection for the out-of-band network for management, and then the in-band network, you know, to stitch everything together. And so you've got this cluster of title pods, and you have your guest image. What networking does the guest see? Do they see one NIC per underlying host, or do they see one, aggregate virtual NIC that, somehow slices and dices?
Well, so internally, I've played with LACP in the FreeBSD layer
Yeah.
to stitch NICs together, but that's not something we're pushing as a feature. So right now, we take the the IX interfaces, the 10 gig interfaces. We hide that from the guest.
Right.
These typical server blades have between 1 and 4 1 gig E interfaces
Sure.
built in. So there's a gig E interface that's usually the combined our management channel and the BMC channel.
Okay.
We hide that too.
Right.
And then the rest is available to the guest. So if that particular machine had more 10 gig E, the guest would get it. If that machine had more 1 gig E, the guest would get it.
As individual NICs.
Yeah.
As
Okay.
individual NICs.
Yes. Okay. So if the node has 10 NICs on it, okay, you use one for your resource stuff, and you use one for management, and one for the BMC, and the guest would see 7.
Yeah. Times
From that node, and then this other
And the
node over
union.
here might also have another 7, and so if you had those two stitched together, then the guest, which is running on those two nodes, would then see 14?
Yeah.
Okay.
Right, and what we do is we're doing, the thought process is to just right now with the first release, is we just increment the PCI bus number
Mhm.
as we aggregate that hardware across the nodes. Isn't that right, Mark?
Yeah,
Yeah.
different PCI bus numbers for each node.
Right.
But from the guest point of view, they're all
Right.
local PCI buses. They're just,
Yeah.
Right, we don't present a NUMA or SuperNuma architecture to the guest.
Okay.
This is one of the things we've done philosophically in terms of what the hypervisor lies to the guest about,
Right.
is we claim a completely flat architecture.
And the resource bus is invisible to the guest.
Yeah.
Right. And so our thinking is, if we're doing our job right, so everything's mobile. So the guest virtual processors, which to us are threads of execution, right? We can package up, we call it a continuation. And at the point where we need to temporarily stall the guest because it's referencing a non-local resource,
Right.
the scheduler, right, and what we call our constrained cost functions make a decision. Do we move the memory or the resource to the thread of execution, or do we move the thread of execution to the resource?
Gotcha.
Okay?
Okay.
And so if you think about that, because the thread of execution can move, right, the fact that it's truly NUMA, you can, with a straight face, lie, because what we're going to do is potentially move the thread over to the other node where its distance to memory is now
Right.
1 again, right?
Right.
So that's what's going on underneath the
Okay.
hood. Yeah.
and we move things very fast and dynamically.
Right.
So the goal is to create the working sets dynamically
Right.
and always keep them up to date.
Gotcha. Speaking of the resource bus, so are you guys, to be able to do this type of live migration of the continuations, you need, I would imagine you need really low latency, or else it's going to get really ugly really fast. So,
A little bit better.
huh? Yeah.
But it does run on Fusion using virtual machines.
Well, okay.
No, I'm just saying, it's amazing how tolerant the guest is. Yeah,
So,
but go ahead.
so my question then, actually, for what I was asking, that actually Fusion would actually be a little bit better, because my question is, because in Fusion they were all literally locally co-located, so latency between nodes is going to be pretty darn low. But when you're going across multiple physical machines across this, I think you said 1 gig or 10 gig resource bus, is that just using straight Ethernet, or is that using something
Straight
like Rocky, or
Straight Ethernet.
straight Ethernet?
It's a zero copy straight Ethernet
Okay.
protocol, so
Nice.
it should be wire speed limited. It's
Nice.
actually not quite yet, but then wire speed for moving a page or moving a processor state is under 3 microseconds.
Good design.
Sounds like-
Excellent.
Sounds like it's actually,
But let me add something, because you said something that that might be misleading to others. In fact, we have almost never seen congestion on this resource bus. And the reason for that is that when we detect that there's a lot of references from a processor over here to a bank of memory over there,
Right.
you wind up moving it.
Right, and then it's local.
It's
Local
adaptive.
again.
Yeah.
So we have the ability to bind multiple ports together to increase the bandwidth. We've never had to do that.
Okay.
Probably when we get into the many tens of nodes, right now 10 gig E seems fine.
And the architecture doesn't require 10 dB, so
Yeah.
if there are
We can go
faster
higher.
Yeah.
things, we
Right.
can use them. But,
Yeah.
yeah. But the key thing is, mobilization is kind of a novel
Yeah.
idea in our thing, that we pull together, we try very hard to pull together things that are working with each other.
Sure.
Multiple CPUs, that's the gang scheduling sort of idea, except spatially too, and memory and even I/O devices. If an I/O device is being heavily used by a group of CPUs, we might migrate them all into the relevant space for a while. And that while doesn't have to be, to pay off, that doesn't have to be very long because you can actually do a lot.
Yeah. And just to be clear, I mean, when Ike and I were presenting this, we had one guy say, well, vMotion takes a long time, blah, blah, blah. It's not vMotion,
Right.
right? We're just moving the thread of execution. We don't have to move any memory. And when that thread lands on the new node, ideally, a lot of the memory it needs is already there. Top of stack, other things will page over, and it'll all just run at speed again.
Okay, yeah, so that's the part that I think threw me. So
Yeah.
you're moving the continuation, so you're moving CPU state and stuff, but you're not actually moving the memory that it's going to be referencing. So when you move the continuation over here and then you start running it, and it's referencing memory that's over here, it's gonna have to go back over the network.
Well, what happens?
Or pull the pages.
Yeah, so what we've been finding so far is that, the usual things you'd expect. So the thread of execution, there's top of stack, there's a few pages. So far in our analysis, it's been less than 30. That when you move that thread, it very quickly demands over those 30 pages, right? But there's other optimizations you can do, for example, for read-only pages or read-mostly pages. And so we take advantage of those optimizations as well to reduce the number of pages that have to get moved over. So as you can imagine, text pages we can replicate across or have them on all the nodes, things like that. It's actually surprising, the active set size is smaller than you expect.
We had talked about actually doing optimization, or actually writing code to handle that.
Right.
Like, do we have to explicitly send this stuff over? And we didn't even have to,
No.
use it, we just pull it and need it.
Right, we just had to have a heuristic so that we didn't migrate back to get to the next page, right?
Right.
If we've made the decision to move, that has a little bit of gravity and stays there for a while.
Right.
So it gets those pages and then gets to work on the new node. That was enough.
What about like a runaway process? You got something that's just eating resources here, you got something to detect that and put a kibosh on it, or?
No, because it's the guest. We let the guest do whatever the guest does, right? So yeah, absolutely. In our testing, we use the LTP, we use a program called Stress, which one of our
Yeah, that's a
vendors,
good
yeah. So we intentionally write software that abuses our system. But remember Ike was talking about locality.
Yeah.
So one of the things I say is that we, in this community, right, everybody in this room, we're all OS, kernel, infrastructure people. We have a mental model about how computers and operating systems and memory management works. And so when we write software, we try not to write crazy software, because crazy software doesn't behave well on bare metal. So yes, right, we use crazy software to test TidalScale, but we find that for the most part, most programmers understand that random, thrashing of memory is bad on any system, so they write their software not to randomly thrash memory. And everybody in this room probably knows who Deming is and locality, and so we are lucky that way, that all the programmers in the world, for the most part, write programs that behave well, because if they didn't, they don't run well. And so well-behaving programs are most of the programs, and they run on TidalScale just fine, right? But yes, you can write a program that is nightmare on TidalScale, right? But luckily, that's not the common denominator.
And it, you know, and all this decision making is all adaptive. There's no master scheduler sitting somewhere. And all decisions are made locally on the servers.
So when I spin up a process in this in the VM, is it evenly distributed throughout the pod, or is it?
Depending on its memory demands, it may end up being distributed across the pod, yes. So if that process, so for example, a SQL database or R, has a data set that's bigger than a pod, right, stretches across, a server node. So the pod is all of them together, let me be clear. So the cluster, we call it a title pod for marketing reasons, right? We want to go to trademark or patent. Trademark. So the cluster has servers, and an individual server might have 128 gig. And you may be running a 500 or 2 terabyte data set. So that will spread across all the individual servers in the pod. Yes. Right? And then ideally, what then happens is the activity of the program builds up those working sets, right? And then we let the thread of execution wander around as it needs to, right? That's the cool part of what ends up happening, then it's operating at speed. Right? So in big data, there's inevitably a load problem, right? There's nothing we can do to speed up putting a terabyte in the memory or 10 terabytes in the memory. That's going to always take a while. But it turns out a lot of this type of work is long-running processes. They put the data in the memory and then they spend a lot of time analyzing it. Right? That's where we have a good advantage. Any more? Yes.
What happens with a component failure?
Today, you will eventually crash. I say eventually because what that looks like to Linux is some amount of DRAM failed, and some, depending on where your CPUs are at the time, some number of vCPUs failed. And right now, it's surprising, but Linux may limp along for a little while, but then it crashes, right? And we're currently not worrying about that. We have stuff on the drawing board that we think we can do to address node failure. But the easier stuff would be to have hot nodes available, and then we can, as a potential node failure alert is coming in, as hardware tends to do nowadays, an uptake in, say, increase in ECC errors or some other thing that makes you worry, we can actually migrate the memory, migrate the threads of execution off of a node. That's a future feature. It's not 1.0. Tom. And then you could take things out of service without shutting down the guest. What I hope to do when this is shipping and people in the community like yourselves are using it, we'll start working on the hot swap capabilities in the guest, right? Because that's really how we make that work really well, is to have the ability for the guest to survive losing a CPU or lose a bank of memory, kill the processes that are in that bank of memory, right? Make stuff available and then let it keep running.
Yeah, it's worth pointing out that there is activity, at least in the Linux world, and I'm not quite sure in the FreeBSD world, but it would be nice if it did, if it was interested in this really large market, for the operating system that will be running on top of us to respond to emulated failure. So basically, if we see a processor fail while we're running something on it, there's not much we can do unless the operating system is prepared to already have a hot spare processor. But as even in the single big machine world, that's why the Linux guys are working on it. That is doable, and it can be handled by the operating system as long as you add a little bit more functionality to both have, you know, some kind of checkpointing of memory and some kind of checkpointing of processing.
Yeah, but we're not even,
Actually, you can handle
yeah.
online failures, and so we're actually in the position, and this is the longer term, where given the architecture we have where everything can move around, and the fact that we're faking stuff to the layer above us, we can just tell Linux a lie that basically said this processor failed. Do what you do. Right now, these operating systems that we run don't handle that well. So if you want high availability, you buy 2 TidalScale.
Something that's been very surprising.
Well, no, I was just going to say, I mean, Netflix does not run on one server, right? And Chaos Monkey and other tools have taught us that the way to have reliability is to design your application layer to be resilient in the face of server failure, individual node failure. And so if you think about TidalScale as just another node in that application architecture, we already have phenomenally resilient application architectures that survive single node failure. In our case, the single node may be 1 or 10 terabytes or bigger. But if you're really interested in resilience and you really need this kind of thing as nonstop, right, then deploy multiple TidalScale nodes with that resilient architecture on top of it, just like you do today.
Multiple TidalScale machines.
Right. Yeah.
So one of the things that's been very surprising to some of us is the stuff is, because there's no shared state at all between these systems, each of the servers just runs and things just naturally recover from software problems that we've seen. And the downside of that is that a lot of the performance issues that we are seeing right now have been masked for a long time because things recover on their own.
Inside the distributed network.
Right.
Yes.
Yeah,
It's amazingly resilient without doing any serious work.
yeah. It turns out we can make mistakes about where to send memory. We can make mistakes about where to send a processor. And those mistakes are invisible to the guest. The guest just keeps running. We know from performance analysis that we did a dumb thing, but the guest just keeps running, right?
I don't know if I'm hearing what I want to hear.
Okay, what do you want to hear?
What I want to hear is that if a node in your pod has a problem, they can add another node, the threads, processes, whatever, get migrated over
Yes.
transparently.
That's
You take the other one off,
Yes.
because you know what? I mean, that's why I want to use it,
Yeah,
right?
no,
I mean,
that's-
that's the whole reason.
that's the eventual.
I've got an I've got EC2 instances that have been running for 5 years, and god damn it, I've had to migrate those fuckers like 5 different times, at least once a year.
Harry and I
gotta do
Harry and I have
another
lived that
image.
pain.
Yeah, constantly.
Yeah.
Why?
Yeah.
You know, oh, because the hard drive, you know, oh, we got a resource failure on one of the VMs that you run on. Like, why is that my problem,
Right.
right?
No, I think you bring up a good point. So to answer your question,
I know
architecture.
they're using Sun's, what was it, whatever their new stuff was, but anyway, sorry.
So that's not a 1.0 feature, because we don't need it for 1.0, but it is in that feature, what we call a virtual node, where we can live push everything off a node onto a new node without restarting the guest. That is on the plan.
We have
But that's different than, but that's different from sudden death resiliency, where there's like a gamma ray that fries a computer at random. That's different, right?
Why don't you mention the under provisioning, over provisioning?
Well, that fits into what you're talking about. So if you had, so if you look at wherever my mouse is, let me go back into
Since we're already lying,
yeah.
Right.
no,
Right, why not, over provision?
over provisioning.
Yeah, sure.
Yeah,
No
so
problem.
you could have this rack of 30 blades, right? But you only tell the guest about 29 blades worth, right? And then we can transparently go, oh, blade 14 is failing, move all of that to blade 30, right? That's what we're talking about being able to do. And you would not know that happened. The guest would not perceive it, right?
There's a reasonable amount of resiliency. There's basically two standards. One standard is the, sort of 5.9 standard that certain kinds of always-on operations require. That's not a 1.0 feature.
Sure.
But if you think about it, any one kind, for example, one of the reasons we did dual 10 gig Ethernet connections for a backplane is that one of the most frequent failures of hardware is actually the cable coming loose or getting corroded or whatever. And that, if you've already got a fallback, that particular component failure doesn't cause you an immediate problem, but you might want to fix it. So that's why you might migrate all the work from that node to another node,
Right.
take that node out of service, change the NIC or whatever.
Or all the nodes have dual power supplies, one power supply fails. Okay, migrate all the work off that node, pop it out, pop a new one in, right?
And all that can be done with that. It will be, well, actually, will be.
Will be.
That's in the plan.
That's in the plan.
Will be
Yeah.
done,
Yeah.
and is doable in the current architecture because everything can be moved. Similarly, disks, if you've got a basically RAID disk environment, however you construct your RAID, you can either replace the disk drive right away, or you cannot replace it and say, okay, I'm going to swap the stuff off the RAID same way.
But it's
But
hard-
a sudden vCPU, a sudden physical CPU failure when that's running guest code takes more than what we're committing to do, because if you think about it, you basically have to go back to the last working state that was in that machine, which is a checkpoint, and restart it. So that's a longer term plan. It still fits into our architecture.
But it may not be, the market may not demand it.
Market may not need.
What you're asking for, we want to do, the market would demand it. But the tandem lockstep fault tolerant programming, we don't see this market demanding.
So basically, the idea here is, as far as that level of fault tolerance right now, is it's up to the guest to do their own checkpointing and,
Yeah.
if necessary, restore from checkpoint. Okay,
Yeah,
and that's a perfectly reasonable thing to do.
yeah. Because for the big data people we've been talking to and the SQL people we're talking to,
Yeah,
if they're serious about their SQL, they're already doing that.
yeah, no, totally.
Let me make it one more comment. It's hard to have a scientific discussion about reliability without really characterizing the failure modes you're talking about. Failure modes are very different. If you look at our architecture with the system image, and you look at the distribution of failures between hardware and software, it turns out hardware is far more reliable than software. And we've got a lot less software running in a single system image than there are hardware pieces. So you can actually do a computation that says we're going to be more reliable rather than less reliable. You have more nodes. But again, we always get the question, and we don't have a super solution. Larry Ellison would tell you to buy another Oracle machine.
Right, sure. That's not another note on it.
Yes. But I like what you're saying, because we've seen that ourselves in AWS, in the resources we use there, that
Right,
because they're changing the rack or whatever they're doing.
right.
Yeah. Yeah. And that's avoidable. It's absolutely
It is.
avoidable.
But there's two different ways of thinking about it, right? Just to add one more point here. You can try to do fault tolerance at the application level, and you can try to do fault tolerance at the systems level. And different people come up on different sides of that question. So Netflix will do it at the application level, and other people will do it at the systems level. They're both valid. I don't know how it's going to turn out over the next 10 years.
Netflix is right.
Pandering to the audience.
That would have been my opinion even without him sitting here. Because the application knows what it needs to replicate. Well, we're systems guys, right? We've tried to do this. It's hard to do resilience in the OS for all possible user applications. That's really freaking hard. But the people who know their application sometimes get it wrong, but they're more likely to get it right. Right? Oracle's gotten it right. Netflix has gotten it right.
Commits and rollbacks.
Yeah, you know. It's easy, it's, in a way, it's easier for them to do it than for us. Okay. I'm preventing people from drinking beer, so I don't want to do that. Yes?
What sets you aside from your competition?
What competition?
Well, alternatives. So we're less worried about someone doing exactly what we're doing as we are the alternatives to doing what we're doing. Right? So one thing Ike has thought a lot about, and has a very great piece of the presentation he does, is why doesn't Intel just put us out of business? Right? You know, Intel could build a new processor architecture so you could stuff 20 terabytes into a system.
It's called mainframe.
Well, it's a supercomputer, people do it, but it turns out they're not in the memory business. And so if they do that, all they're doing is transferring value to the memory makers. They're making Samsung wealthier, for instance. So, you know, Intel could do this, but they have an economic reason not to do it. Another thing you could do is you could take a single 128 gig system and you could put 100 terabytes of flash on it, right? People do that right now. We happen to be 10 to 100 times faster than flash, right? So that's why, right?
Right.
You know, or 1,000 times faster when it's running in locality. But I'm taking in the overhead of you're not always local to memory, right? So what other alternatives are there? There are people working on alternatives. You know, we'll see, you know, what is it, the company SuperNuma?
NumaScale.
NumaScale. You know, there's people out there, but first of all, we're all we're pure software. You take your commodity hardware you already own, you turn it into a scale-up computer, as big as you need. When you're done with your job, you reboot a slightly smaller one, or you reboot a bigger one. The software eats the world argument is also on our side, right?
So here's a thought experiment. If you go to the Dell website and you try to configure the largest Dell server that you can configure, it's a 6 terabyte DRAM machine.
Might be up to 12 now, but they're very expensive.
It's going to be, yeah, it might be up to 12 now, but whatever it is, let's assume it's 6, because that's when we did it last year.
Yeah.
With a 6 terabyte machine, it's going to cost you $470,000 without any storage. And that'll get you 60 cores. Now, if you try to configure a 6 terabyte TidalScale machine, with our software costs, it's $187,000 and you get 200 cores. The 6 terabyte Dell system is the end of the line. So they'll come out with fancy memories. But the TitleScale 200 core system just adds more if you need more. So no matter how you look at it, it's better. Every time you add another node, you're increasing the number of paths to memory. You're adding more PCIs, you're adding more NICs, you're adding more hardware.
Yeah, and it's a 2P system, right? That Dell system is a 4P system, right? So it's actually not as fast as it seems, right? For those of us who've experienced this strangeness that when you go from 2P to 4P, you slow down, right? Your path to memory on a 4P system, because you're going through QPI a high percentage of the time, your cache misses are actually more expensive than you expect, right? So 4Ps are not a big performance gain on a 2P. In fact, some would argue they're a performance loss.
Actually, it's not just the cache misses.
Yeah,
The contention on the QPI bus for the snooping is high enough that it actually caches.
Yeah, so all of our, most data centers have figured this out. That's why they're all built out with 2P systems. So all of our nodes are 2P, right? You pay a price when you migrate, but now you're running at 2P locality. So it's an interesting thought experiment.
Yeah, so we have a good shot. That's really the way to.
Yeah, we have a really good shot. The price is right. The performance is looking good. Go ahead.
That brings up an interesting idea.
Yeah.
Your system might actually be more efficient than the NUMA sharing that goes on between two socket or 4 socket systems like that. Have you thought about running your system like on each of those and having the QPI as a very, a sort of a lower cost network connect thing to.
QPI is a
you could
resource
probably,
bus.
the way you're doing it, you could probably outperform those guys.
Yeah. Well, that'd be more of a partnership play with a Dell or an SGI or HP or somebody, right? Because we would need the hardware manufacturer to work with us.
No,
You don't think so?
No,
No,
I
we'll
mean,
see.
you just run each of those. You don't make the CPUs go out and talk to the other ones. If you're running on the bare metal, you can do that easily.
That's what 3D did with Hypertransport, actually.
Yeah.
They built an FPGA and talked to Hypertransport, which is the AMD equivalent of QPI, and they didn't really make it.
But what I'm saying is that the way you were doing it, if you incorporated that in the way, you think of it as just a different, faster network, you might be able to.
I think I get what you're saying, and to be honest, we haven't thought about that.
No.
But what you're really saying is take say a 4-piece system,
Yeah.
and run.
Break it in half somehow.
Two
By
sets
four.
out of 2 halves or 4.
Yeah.
And then use our protocols by sort of making memory calls, but
Yeah.
only when we need to.
Right.
Right, just do the same thing
It
as
would
you're doing
just
on
be
the
smarter
network,
parts.
except use that interconnect, and then just think of each of those as sort of like lower cost versions of the big network, and let it optimize itself the way it does now.
Yeah,
I
so
think
that would be an example of what we kind of waved our hands about, which is that we can replace the 10 gig Ethernet with better things.
Yeah, I was mainly thinking PCI Express.
Oh, yeah, but that would,
Yeah.
that would be a hybrid one, where you have, because the really fast things are always gonna have a small number of connects.
Yeah.
And then you're gonna go slower out to more connects, so.
Yeah.
So if you could balance that in your software, you could have it do the, from what I understand what you're doing, you're just sort of letting things pull the resources to where they ought to be.
Yeah.
And you could introduce that one into the same thing, and I suspect you'd outperform the NUMA architectures that people are building into the OSs.
Yeah, we certainly think so.
So theoretically, and I think like even could shoot me when I say this. Theoretically, one could talk about the overhead of the TidalScale hyperkernel as running over guest. But there's nothing theoretically to assume that it's going to be slow. It could be faster. And that gets to what you're saying. All of our stuff is very dynamic. And so, in effect, the execution of the application drives the scheduling strategy. Not a scheduler that has thought about all this stuff in advance, is doing
Right.
the best job it can.
Yeah.
In our case, the execution of the application is driving the scheduling in a very direct way.
Yeah.
I don't know if that makes any sense.
Well, and the execution of the application drives
I think
locality.
it's going to work. See, what I'm saying is, I think it's going to work better than all the other strategies these guys have been trying to bolt on to their architectures. So, you might want to think about that one.
It's a good idea.
anyone has clustered virtualization.
Yeah, the direct competition is not really there. I think that what's interesting when we were raising money, it's partly because people believe it can't be done.
Right.
So why try?
Yeah, good.
Don't! You guys who think it can't be done shouldn't get in the way of, say.
Well, we found VCs who believed in us. Obviously, that's awesome.
You want to tell the slide story around that?
Oh,
Which one?
There's different names and stuff.
the Bain Capital,
Where is application slide?
so, let me,
All right.
so.
This one, yeah.
No.
Remember
All the software.
Word doodle.
Oh gosh, yes.
So I'm
Yeah.
presenting to Bain Capital in Boston, and I put up this slide that Harry actually created.
My fault, sorry.
MySQL, Oracle,
As a tag
R,
cloud.
Neo4j, a few other things.
Yeah.
And I said, all this stuff runs. And, I left the meeting, I thought I did a pretty good job. And I went off to Washington for some other meetings, and they called up and said they want to come and see it in action. I said, sure, go ahead. So Harry hosted them, they come in and they say, well, we want to install Apache, was it?
Yeah, Apache.
WordPress.
WordPress.
And so the guy comes in and seems to know what he's doing. Well, maybe you should take it from there. I mean, you were the guy, so.
Well, Michael and I were, I was, it wasn't me.
Yeah, but Harry booted up a guest, so just like I've got a pod running here, right? So Harry boots up a guest, logs him in, gives him a prompt, and we all step back, right? And the guy starts doing yum and this and that, and he's downloading software, he's building it, and it takes him, the usual thing, it takes like 15 or 20 minutes. He gets a web server up, and WordPress is running. And he's going, how come you didn't have WordPress on your slide?
And Harry says, he wrote the
I
slide.
didn't want to make the slide too busy.
So everybody cracks up laughing.
But then Enrique, it was Enrique, goes to me, he says, well, what runs? Or he says, what doesn't run? And I said, nothing. Everything runs. And that was that.
Nice.
Right? But,
And they wrote a check for $4 million.
and they wrote a check for $4 million.
Well, I guess we're getting near the end here, right? We got cleaning people coming at 9? Is that right?
Well,
9,
shortly
9:30?
after.
Okay.
But Michael, thank you for an awesome 15 minutes.
Yeah. Thank you for your time.